All right. Yeah, test number 2 is planned right now, excuse me, right now for March 17th and 18th, which is, what is that, a Wednesday and a, yeah, it's a Wednesday and Thursday. So I wasn't sure, I mean, module 6, we should be able to get through it this week. And then I left all of next week open for review. And let's see. Oh, yeah. And so I scheduled the test accordingly. I also updated the course schedule. So if you clicked on this course schedule, which I don't remember if it opens in a new window or not. Yeah, I had forgotten to put the date in here for some reason for that. Don't tell me I messed it up. Oh, I messed it up. This should be 317. Now I have to edit this again. 317. All right. Well, one more thing to worry about. Let me write this down. 317. There's too many places to put dates online. It's much easier when I give the class or a test in class on paper. And all right. And then tomorrow is what's called all-purpose day. I don't know, you may have heard it mentioned in some of your other classes. I don't know if anyone's holding class, but we're not supposed to. However, the way they have it set up this year, maybe some people decided to, because normally on all-purpose day, we do like a NCCC informational day. So, you know, people from high schools come in and we do like an open house, basically. Obviously, we're not doing that in person this year. So most of us are doing some kind of Zoom, you know, admissions is doing some kind of Zoom thing. So most of us have things scheduled for that day. So I won't have office hours tomorrow because of that. And then let's go to the modules. Yeah, so what I did is module 6 is open. And that has, what does that have? Oh yeah, that has a PowerPoint in it too. I'm just going to talk about this PowerPoint at some point later on in the chapter or the module. But you know, same setup as before, right? I've got the PDFs that show what the module covers, you know, the reading, some of the applied the concepts questions, which again, your homework comes right from these questions. The worksheet and the handout, we'll probably do some problems from the worksheet. Yeah, maybe we won't get it today, but we'll get to it soon. And then the supplemental PowerPoint. Let's see what else. Video and lecture notes. I'll post them. Oh, this is a supplemental video. It's, what is it, NPR? I can't remember what the, oh, PBS, yeah, NPR, PBS, yeah. NPR is the radio one, PBS is the, this is the TV one. But this covers all of work, energy, and power. So you might want to wait until we're done with the notes, and then you can watch it as a refresher. Mod 6 homework is reading and questions, and the Mod 6 quiz. These should be due again Sunday and Wednesday. Let's look. March 7th, yeah, so the homework's due March 7th, which is Sunday. And the quiz here should be due that Wednesday, which is March 10th. Yes. All right. So that's Mod 6. The other thing I want to point out, we're not really there yet, but I just want to let you know that it's here, is the Test 2 review and test material. So what I did in this folder is I just put the review packet up for test number 2. And then the formula sheet. The test will also show up in this folder. Let's see, test 2 formulas. This is just a reference sheet for test number 2. Variables that you'll need. You know, it's a lot of motion and force. So all that stuff is in here. And we'll go through this formula sheet when we do review. Let's see. All right, so Wow, that's yeah. So back to module 5, which is like what we're on. We're just going to wrap that up now. Let me close this. Open my document camera. All right.
Excuse me.
Well, was there a question?
Yeah. What about the module 5? It is thread for. It's an example about the Newton's law. When is the due date?
Okay. Hold on a minute.
Because there's no due date.
Because all right, you want to know what the due date is for. All right. Again, you know, in the calendars here. You wanted the due date for which assignment in module 5?
It is an example about the Newton's law, so we need to write an
Oh, yes, this one.
kind of example from.
Right, this is due on.
Yeah.
Okay. Go ahead.
Because it's no due date on this assignment.
Yeah, I know. It's in the calendar.
Okay.
I don't know why with discussion forums it doesn't show a due date anywhere. Like if you click it, it doesn't show. Why can't I get out of student preview here? Maybe because these. Okay, there it goes. All right. So yeah, I don't know. It's some kind of weird quirk in Blackboard. I have no idea why it's not. I might have to go in and type it, but it's due. It's due 3/4. Newton's laws discussion board. So that's due on the 4th here. All right.
Okay,
what I did. Oh, what I did here. Yeah, I don't know why it does that with discussion board. I spent, I don't know, 30 minutes one day looking for a place where I could put the. I mean, I guess I could type it in, but I'm looking to try to find the place where it is, and I guess the only place it shows up is the calendar. This is, I can find it. This is the last page of the handout for, is it the last page? Yeah, last page for module 5. So we'll be wrapping this up. And what I did here is I just put together some Zoom polls for this. So each situation is Newton's first law, second law, third law, or law of universal gravitation. So what I'm going to do here is I've got a poll set up which has these options. So first, second, third, and Newton's law. So let's start with the first one, letter A. A car pulls a trailer and the trailer pulls on a car. So why don't you go ahead and choose on this poll which of Newton's laws you think this describes. First, second, third, or law of universal gravitation. And oh yeah, I put a little note in each one to remind you of what they are. So yeah, Newton's first law, law of inertia, right? Object in motion stays in straight line motion. Object at rest remains at rest. Newton's second law, force equals mass times acceleration. And the third law, action, reaction, right? For every action, there's equal opposite reaction. And then the law of universal gravitation is basically a force is proportional to the mass of the two objects divided by the distance squared between them. I didn't write the formula there. Maybe I should have put, oh, we'll be fine. All right, what do I got? 70% of the vote, or 70% of you voted, that's it. Car pulls a trailer, the trailer pulls on the car. So we're doing letter A. It's been about a minute and a half here. Oh, there's still some people answering. Another 5 seconds. All right. Let's see, we got Newton's first law, second law. So Newton's third law, action-reaction pair. That's the correct answer. A car pulls a trailer, the trailer pulls on the car. So that's the every action, there's an equal and opposite reaction, right? The car pulls on the trailer pulls on the car. That's that's the equal and opposite reaction. So let me write that down on the screen here. So I'll just write third law. And so this could be the action. And this is reaction. All right. Okay, let's go to letter B here. I'm going to relaunch the poll. A dumbbell sits on the floor of the gym until someone picks it up. Which of Newton's laws, 3 laws, including four if you include the law of universal gravitation? It sits on the floor until someone picks it up. What is that referring to? Voting faster this time. I'm talking less too. All right, give you like another 5 seconds. I think there's about 21 or 22 people participating anyway. Yes, Newton's first law, law of inertia. And in this particular case, right, the dumbbell is an object at rest, right, remaining at rest. Till acted upon by an unbalanced force. So I need more room here. Force comes along. Right, that person's exerting a force on that dumbbell to get it into motion. So that's I mean, this is first law. It's the first law. It's inertia, right? The dumbbell is sitting on the floor of the gym. The object at rest is remaining at rest unless an unbalanced force comes along. All right. Let's relaunch the poll here, and we'll do part B, which is you apply a force to the pedals of, oh, that's typo, your bike to accelerate yourself from 0 to 10 miles per hour. So which of Newton's laws is this? You apply a force to the pedals of your bike to accelerate yourself from 0 to 10 miles an hour. Oh, I didn't launch the poll. I'm sorry, guys. I forgot when I relaunch a poll, when it's already taken, it gives me the option. Are you sure you want to do this? It will clear the results. Oh, this is on this. This works. almost a couple more people maybe. I'll give you till 1 minute. It's a pretty quick one. All right. Yeah, so it looks like most people have said Newton's second law, which is what the intention was here. So this is the second law. Force equals mass times acceleration. And acceleration is directly proportional to the force applied. Now, something like the third law would have been, worded something like, you apply a force to the pedals apply a force to your feet, or the bicycle applies a force, the rear wheel of the bicycle applies a force to the ground pushes back, right? That would be a third law type statement of this. But here, the implication is that I'm trying to tie force here to acceleration for the second law. All right, let's see. Let's go with letter D now, which is, as a space probe approaches Jupiter, the effect of Jupiter's gravity on it is inversely proportional to the distance from Jupiter. So which of the four laws, well, 3 laws plus lug, is that? What is that referring to? Well, on letter D, I think some people are coming in a little late. Sometimes I pull the attendance for a class and there's like one person listed 3 times because they kept getting booted out. I'm like, oh wow, they having internet troubles today. All right, let's see. Go another 10 seconds here. All right, and most people got this. It's law of universal gravitation, right? So let me write that here. L-U-G, lug. And remember the actual equation is F equals, well, F of G, force of gravity, is G, you've got M1 over, or times M2 over distance squared. So everything remaining constant, the force of gravity is inversely proportional to 1 over distance squared, right? So that's where it comes from the law of universal gravitation. All right, last one here. Let's see. A space probe out of fuel and leaving the solar system will continue on unless acted upon by another force. So which of the 4 laws is that referring to? Laws listed. screen. So I didn't print them. All right. Let's see here. Let's review. Yes, not too many people chose. Oh, just one person chose lug. This is first law. Yeah, so most people got that as well. So Newton's first law. Newton's first law. Inertia, right? Space probe in straight line motion remains in straight line motion unless acted upon by another force, right? And so this was important too. It's out of fuel, so it's just going under its own inertia, right? It's just continuing on. And I think I just realized I can't find the printout for module 6 stuff. Yeah, so I'll print it when I get to it. All right, so this basically wraps up mod 5 with Newton's laws. I mean, you should be all prepared to take the quiz and complete the discussion board assignment as well. Are there any questions about any of these? I believe on the test, when I give you these, I give you a brief summary of Newton's laws as well. But you should know them. And you can remember them quite simply again by how I have them in the poll, right? Inertia, F equals ma, action, reaction, and then, well, universal gravitation. That's not one of the three, but you will be given, in the context of that, you will be given a formula anyway. Yeah, so that's Newton's laws of motion and universal gravitation. All right, so what I'm going to do here is switch gears. And I'm going to go to start module 6. Stick this in the folder. And for module 6, we're going to be talking about energy. And this is really not that far from what we were just talking about, forces. Let me just put mod 6, energy. This is also chapter 3 still, or no, sorry, this is chapter 3. All the stuff we just covered, module 4, I forgot how I split it up. Module 4 was module 5 was chapter 2, as was module 4. This is now chapter 3 in your textbook. And before we get into, well, let's be very specific first about a form of energy. And what I want to talk about is work. And what is work? Well, work occurs, or this is what occurs when a force acts, or is exerted through a distance. Let me write some variables here. W is the variable, and the units, so let me just put a little variable. The units of work are joules. And we saw this with kinetic energy, right? Potential energy. Those were the same units. So work is a type of energy. And the general equation for work is force times a distance. So force times distance. I mean, we already covered this somewhat with, well, we covered the units a little bit with potential energy. And the units on this are Newton times meter, right, which equals a joule. Joule. Not like the jewel you buy at the jewelry store. So one example, I want to give an example here, just to clarify things, right? Lifting a book through a distance is doing work. Holding it, or holding a book, let's just write that out, holding a book in a given position is not. So work is defined by applying a force and exerting it through a distance. So if I like push against the wall, if I go to campus and I'm like pushing against the wall, one of the buildings, right? I'm gonna look pretty foolish. But also I'm not doing any work, right? I'm just standing there pushing against an object that's not moving. That is not work. That is just standing there, you know, pushing, I'm exerting a force, right? So it obviously takes me energy to make my muscles exert a force, but that is not doing work. To do work, you have to have a force acting through a distance, right? Work equals force times a distance. The more, you know, for a given force, right, the more distance you act, you know, you apply that force over, the more work you're doing. Or the short distance, right, the more force over that distance, the higher the work. So that's work. And energy is basically the ability to do work. Let me just expand on this again. Oops. In every process, there is an exchange of work and energy. Let me just write this as work and energy. So work can be stored as energy, right? And then energy, stored energy, can be used to do work. These two concepts have the same units, right? Joules. You can take let's think about this. We're going to get into more examples later on, but you know, one way that we talk about, especially with renewable energy, you've probably heard this discussed, right? How do we store the energy from solar and wind when the sun's not shining and the wind is not blowing, right? And there's a lot of different ways that you can store that energy. And what you're doing is you're taking work and you're storing it as energy into some device like a battery or pumping water, right? That's one way they store energy. You pump water up in elevation, and then that stores, you know, you're converting work into stored potential energy, and then you drop that water through a turbine like we do in Niagara Falls, right? You convert it into work, which is basically, you know, then generates electricity. And we'll get into that later on when we talk about like generation of power or electricity. All right, so the next item on here that makes sense to talk about is power. So power is just the rate at which work is done, right? The rate at which work is done. Also, because work and energy can be interchanged, right? It's the rate at which work is done, but it's also the rate at which energy is converted. And the units on this, let's see, power, well, P is the variable, right? So let's write this down here, power. And the units on this are, oh, this is going to get confusing. W for watts. Let me write this out here. Power is equal to work over time and the units on this are joules per second. So that's what 1 watt is. 1 watt is equal to 1 joule per second. Do I have room to fit this in? Probably. A 60-watt light bulb, which I'm not sure if those even exist anymore, converts 60 joules of electric energy to light and heat. In 1.0 seconds. So that's what watts means in the context of energy conversion, right? If I tell you something is 100 watts, it's converting 100 joules per second of energy into something, right? And in the case of a light bulb, you convert that electric energy into light and heat. Let's see. The aside here. Let me see what my next page looks like. Oh yeah, I'm supposed to do the examples. Well, let's say US units. 1 horsepower is 746 watts. All right, I want to do an example, but I didn't print out the form, so I'm going to do that right now. Oops, I can't see anything. Let's see, mod 6 worksheet. I'll go back to the notes in a minute.
Excuse me. How
Yep.
about the LED bulbs? So they doesn't produce heat. So or produce bulb.
Oh, they produce heat. They're just more efficient at converting electricity to light. So for a given amount of wattage, so if you go to the store and you buy a, hold on a minute, let me just print this out because I don't want to mess up this. Oops, that's not what I want. Mod 6, okay. Yeah, so an LED bulb, if you go to the store, right, you'll see, you might still see on the bulb package, it'll say equivalent to 60 watts, right? It's equivalent to 60-watt light bulb. But if you look at the actual rating on that LED, it's not 60 watts. It's going to be something like, 10 or whatever the, in fact, you should say on the package what the rating is for the power. The problem is that for so long in the US, we've used watts interchangeably with how much light something gives off, right? We're just used to that. Oh yeah, 60-watt light bulb. Really, the light that's given off is in lumens. So an LED is more efficient in turning electrical energy into light. So it actually uses less power to produce the same amount of lumens or candela, depending on the
Okay.
system.
Okay, got it. Thank you.
Does that answer your question?
Yeah, thank you.
Let's see, 1, 2, all right. I'm printing out the worksheet. I could have sworn I printed this. I'll probably find this in some pile somewhere. So let's go and let's do some examples in between. A force of 200 newtons is used to push a table across a level classroom floor over 3 meters. How much work was done on the table? All right, so what we're doing is we've got this table standing here, and it's on a level surface. And, well, I already started in blue, I might as well finish. We've got 200 newtons of force, and we're pushing this table through 3 meters of distance. I'll draw another table over here. Well, how much work was done on the table? So work is equal to force times distance. And that's just 200 newtons times 3 meters. So we wind up with 600 Newton meters. So the work is 600 joules. And notice we don't have to worry about significant figures. We've got 1 and 1 and 1. So we're pretty much okay here. So that's the work. Very simple example. Work is force times distance. Newtons times meters gives us joules. Example 2 is a conversion problem. Oh, in fact, example 3 and 4 are also conversion problems. Oh yeah, they're all different flavors of conversion problems. Let's look at example 2 here. How much horsepower is a 250-watt light bulb? This always makes me laugh when I do these problems because I think, oh, imagine going to the grocery or the hardware store and looking for a bulb and horsepower. It's a very humorous thought. So let's see, part A. 250 watt light bulb. So, oh, let's remind ourselves over here. 1 horsepower is 746 watts. So what do I have? I have a 250 watt light bulb. And I want to convert that to horsepower from watts. So I know 1 horsepower is 746 watts. This gives us 0.335 horsepower. If you use significant figures, 250 watts equals 0.34 horsepower. 2 sig figs, right? 2 sig figs. The 746 we're taking it as an exact conversion. So we're limited by the number of significant figures in the 250 watts. So if you want to buy a 250 watt light bulb, go to Home Depot. Say, do you have any 0.34 horsepower light bulbs? They'll look at you like you've got like some kind of, I don't know, second head, third eye, whatever. Part B. How many watts is a 230 horsepower car? So now we're going to convert the other direction, right? In this case, we've got a 230 horsepower car, which is not so unusual, right? I mean, it's kind of, it's not your standard car, right? 230 horsepower is a, you know, not your standard 4-cylinder car. So now we've got 230 horsepower. And we want to convert horsepower to watts. You know, I didn't show my units canceling up here. I'd like to do that. And in this case, we want watts. And we want to eliminate horsepower. So up here now, we've got 746 watts is 1 horsepower. Right, the horsepower is canceled. And we have 171,580 watts. If we look at significant figures, again with the 2 sig figs, we can write this a number of ways. We can write 170,000 watts. We could write 170 kilowatts. We can also write 1.7 times 10 to the, wait, 5th, 1, 2, 3, 4, yeah, 5 watts, right? So if anyone ever asks you, what is the power of a 200 horsepower car in watts, you can say, well, you know the conversion factor. So there you go. So next time you go to the dealer, go to the dealership next. Anytime you're looking for a car in the future, like, I really want my car to have this many watts, and they'll look at you like you're insane, or they'll try to sell you an electric car. All right. So any questions about these 2 examples?
It sounds funny, but in Europe they start to produce the car in a, they measure in 9 horsepower by in watts.
They measure 9 horsepower by watts?
Yeah, now they started to measure in
oh yeah, I was going to say in a later example, I usually think of that, how, in the US we're so used to dealing with horsepower, but especially electric motors and pumps and stuff, a lot of times they're rated in watts. And you go to Europe or China or other countries, other parts of the world, right? They manufacture things, they typically rate things in the metric system, right? So they'll typically rate things in watts. Yeah, so that's a good point. Even internal combustion engines. However, they'll convert over because still a lot of the market for vehicles is in the US and Canada. And well, I don't even know if Canada uses watts or horsepower.
They use
Vehicles
maple
are
syrup.
odd. What's that?
They use maple syrup.
They use maple syrup, yeah. How many how many gallons of maple syrup is that? All right, here's another one. Motors rated in 12.5 horsepower. What is this in kilowatts? So we just did an example similar to this, but now we're actually, we've got horsepower. We're going to report it in kilowatts. Same factor, 746 watts per 1 horsepower. Now, if you don't want to wait till the end, you can always throw in your kilowatts here, right? I know this is going to give me watts, so I'm going to divide by watts and get kilowatts, right? What's the equivalence here? 1 kilowatt is 1,000 watts, right? So this shows you how you're dividing through. First, I'm converting horsepower to watts, and I'm converting watts to kilowatts. So I'm multiplying by 746, then I'm dividing by 1,000. I wind up with 325 kilowatts. And with significant figures, this is equal to 9.33 kilowatts, right? We've got 3 significant figures in the 12.5 horsepower. And then down here, a motor's rated at 18.5 kilowatts. What is this in horsepower? Again, this is just working the opposite direction from up here. 18.5 kilowatts is what we have. We want to get this to horsepower, but our conversion factor is in watts, right? 746 watts. So the first thing I'm going to do is I'm going to convert this into watts. I'm going to say watts on top and kilowatts on the bottom. Again, equivalent, these are just equivalents, right? 1,000 watts is 1 kilowatt. And then I'm going to multiply this thing by the conversion factor. I'm going to be getting watts here, and I want watts to horsepower. So I want horsepower, and I'm going to have watts. Ooh. Oh, my alarm just went off. And that's 1 horsepower is 746 watts. Again, you do the math here. 18.5 times 1,000 gives you the 18,500 watts, right? And then you divide by 746 and you get 24.799 horsepower, which is just equal to 24.8 horsepower. 1, 2, 3 significant figures. So that's what 18.5 kilowatt motor is rated at, or a 12.5 horsepower motor up here, right? So now you know how to convert between them. And particularly electric motors are rated in watts, right? Because that's just what we use for electrical systems, even in the US mainly. You don't typically read about horsepower electric, like you don't go out and buy a refrigerator that is refrigerator rated in horsepower. All right, so that's what I have for today. And so don't forget mod 5 wrap that up, finish the homework if you haven't already. There's the quiz on Wednesday, by Wednesday, and the discussion board post for that.
Thank you.
Yep, have a good one,
Thank
everyone.
you. Have a good one.
Thank you, you too.
Thanks. Oops.
Can I be a pain, or do you have a class right now?
I have a class, but if you have a quick question, I can answer it.
I was just gonna ask so I get like the 1,000 watts, over the 1 kilowatt, and then the 1 HP over 746. I'm talking about example 4.
Right.
So we're then timesing that by the 18.5, is that right?
Oops, you can see my screen, right?
Yeah,
Are you talking about this one? Oh.
because I know when we go over it, like we do it all and like I have my calculator out, but then when
Yeah,
I go
think
back.
about this as just- think about this as just two conversions all in one shot, right? The
Okay,
first thing I'm doing is I'm just converting my conversion factor is I know the relationship between horsepower and watts, right?
yeah,
So the first thing I want to do is just I want to get the 18.5 kilowatts in terms of watts. Now you can do this in your head, right? If you remember the prefix kilo is 1,000.
okay,
So that's all we're doing here. 18.5 kilowatts is 18,500 watts,
okay.
right? And then I multiply that value in watts by the conversion factor to get horsepower. So it's just, I don't know, did that explain it or not?
Yeah, it's just showing it, yes.
Yeah,
Yeah.
just showing it. So all I'm doing is, and you could have done this in your head. You could have said, oh, this is 18,500 kilowatts, or you could have done it down here, right? 18,500 watts times the 1 horsepower over the 746 watts, right? That's all this is doing. This is the first step, converting the 18.5 kilowatts to watts. And then the second step is doing the conversion to horsepower.
Okay, thank you. I think I was just confusing myself when I was looking at it all, like, wait, how did I do that?
Yeah, yeah.
Perfect.
Okay.
Thank you. Have a good day.
You're welcome. You too, Ashley.
Bye.
You have any questions, Dana? Or? All right, I'm gonna put this away. I'm gonna end the meeting because I have another class.